Thanks for the introduction. Thanks for all the organizers for making this great event happen. And actually, like this is probably like the third, not sure the second or the third time that I attend a quantum computing session here at IPAM. But actually, this is my first in-person meeting because like the previous ones were both like virtual. But like I'm very happy to be here to deliver the first tutorial on introduction to quantum numerical linear algebra. So like before that, maybe let me do like a quick pose. I just want to like know like the background of the audience. So like how many of you are from like math background or math or applied math or? Okay, perfect. So how many are physicists, chemists, quantum information or? Okay, perfect, great. Yeah, we have a mixed background and that is like what I'm expecting. So actually like during the entire tutorial, I will just like use multiple languages. So some languages are from math, some languages are from like quantum information. I will just like make them like to be there simultaneously. So you can just like choose whatever you want to try to like understand the materials. But like, okay, yeah, let me start with the introduction on the quantum numerical linear algebra. So the topic is quantum numerical linear algebra. So let me start with the text and the a high-level introduction on what the numerical linear algebra is. So like for the classical numerical linear algebra is basically like we are using some like matrix operations to design some algorithms. Like so, for example, like we can use some like matrix multiplication, matrix vector multiplication, or some like addition, or some kind of like other like floating number operations, and then we use those operations, and our goal is to design some algorithms for like some tasks in scientific computing, like here I list like a few on like solving linear system of equations or some kind of matrix factorization. But like for factorization, they're like mostly also for the linear system, and also like some eigenvalue or eigenvector problem and singular value problem, and also like the spectral or singular value decomposition. So those are like some standard texts for numerical linear algebra. So by quantum numerical linear algebra, what we are meaning is that we are trying to do everything on a quantum device. That is like we try to like implement our matrix operations like the matrix vector addition multiplication on a quantum device or on a digital quantum device, and then like we try to design quantum algorithms for this task, like it's like for linear system or for other vectors. So it's like it's a little bit off from the standard quantum information course, because like in your standard quantum information course, you probably will not learn something about linear system or some kind of like eigenvalue singular value transformation. But that is the text of this of today's tutorial. So what is the motivation of considering like quantum numerical linear algebra? That is like why do we really care about that? So what kind of speedup that we would like to expect? So like it is kind of like a very, rough idea on the general speedup that we would expect. Oh, I forgot to mention, so I think Lynn mentioned that before. So please feel free to ask questions, feel free to interrupt me and ask questions. Yeah, I would be very happy to take that. So, okay, this is kind of like a general speedup, but there are some kind of like caveats. So like the general speedup is kind of like in terms of the dimension. That is like in the classical numerical linear algebra, so for example, if we care about some kind of n-dimensional system, so basically like we need to like store an n-dimensional vectors, need to store like an n by n dimensional matrix, and then like you can imagine that. So the cost of this task in classical would be something like at least linear in terms of the dimension, because like for example like the space should be like at least linear in n if you don't have any further structure, and also like if you do like the matrix vector multiplication, which is the core operation in the quantum linear algebra algorithms, and in the numerical linear algebra algorithms, then even for the sparse matrix, you should like do like something at least linear in terms of n computational cost. So that is like what we are expecting in general. But like for quantum algorithms, so actually we are expecting some computational cost to be like polylog in terms of I have the laser. Okay, to be the polylog in terms of the dimension. So in a very high-level perspective, or very or maybe oversimplified perspective. So this is because of the quantum data structure. That is like for n-qubit quantum state, it can be viewed as a 2 to the n-dimensional unit vector, and you will see that later if you're not familiar with this. And also like for many matrix operations, so they are like performed or they are implemented on this little n qubit, where little n is kind of like a log of the capital N. So with that kind of structure, so we are expecting that we can have a possible exponential speedup in terms of the dimension, but there are like many caveats because like the quantum data structure is not the same as the classical data structure, and we have some quantum state which is like not quite useful for extracting classical information, or there will be some other computational overhead. But like at the very beginning, at least like when I first learned quantum information, I just like view, okay, we can kind of like get this kind of like general exponential speedup in terms of the dimension. So that is a good way of starting like thinking of these kind of things. But like, okay, so we are expecting some speed up in terms of the dimension. But for the quantum numerical linear algebra, actually we have some restrictions. So here's like, okay, so like for the restrictions, it's really because like on the quantum device, we cannot efficiently perform all the matrix or all the numerical linear algebra operations. Or by efficient, I mean that I want to like perform those operations with only logarithmic cost. That is, I don't want my cost to be polynomial in terms of the dimension of the Hilbert space. But like here, actually, like we have many restrictions on like quantum devices. So here, I just only list like a few of them. So for example, like for the vectors or for the quantum states, actually like they are normalized under 2 norm, which means that we can only represent some like normalized vectors. So this is like a small caveat because like we only lose some information on the norm. But like if you want some classical information regarding the vector norm of your like of your solution, then probably we have to pay more cost. And another major difficulty or major restriction of the quantum numerical linear algebra is that we can only implement a subset of the operations of the linear algebra operations. So here I mentioned that actually like because like so on a quantum device we are performing some like transformation between a normalized vector, normalized quantum states, which means that so for those types of transformations they should be some like unitary matrices. And even for the unitary matrices, not all of them are efficiently implementable. So only a further subset of the unitary matrices are efficient on certain quantum devices. So like we can see that so now we only have like unitary matrices. Basically, like we have a very hard restriction, and then like we just want to like explore like whether we can still do something meaningful, do something interesting with this kind of subset of the operations. But like in this talk, I will just kind of like talk about like actually like for the general matrix operations, like matrix vector multiplication, actually like we can still somehow implement those operations. But like the idea is basically like we will like embed those general operations in a subspace of a unitary matrices, which is called the block encoding technique. But like this kind of technique works quite well, but it will introduce some actual computational cost. So the third restriction I'm listing here is the no cloning theorem, which is basically saying that if you have an unknown quantum state or unknown vector, so it is impossible to really like make a copy of this state. So this is kind of like interesting from a numerical linear algebra perspective, because if you're familiar with the iterative algorithm, so for example, like in like the conjugate gradient or the GM-RES for solving linear systems, so they are kind of like iteratively finding the desired solution of a linear system. But like when you use the iterative method, so probably you have to use like multiple copies of your current step or even your previous steps to like construct the step size or some kind of direction for your next step. So that is very expensive. Oh, sorry. Making the copies is impossible. So on the quantum, you have to like make your copies at the very beginning. So for all the algorithms, which can be very expensive. So this no cloning theorem is basically saying that so probably like general iterative methods are not directly implementable on quantum devices. But like there are some like special cases. I think I will mention that later in the tutorial. Okay, so here's like a rough summary of the introduction part, or like it might be like oversimplified, but I mean, I think it is always like a good starting point to think something that is simple. So it's like, if you like compare the quantum numerical linear algebra versus the classical numerical linear algebra, so the speed up that we are expecting is that we want to achieve some like speed up in terms of the dimension. But like for quantum, so we can only perform a subset of the unitary operations or a subset of certain operations. But like for classical, we can do some general matrix multiplication or some like copying or even some kind of intrawise information. But the intrawise information is hard for quantum. So my very rough understanding on the quantum numerical linear algebra is basically like the linear algebra algorithms with restrictions but possible speed up. That is, we have some restrictions from a mathematical perspective. We have some restrictions, so we can only implement a subset of operations. But thanks to the structure on the quantum device, we can like obtain some speed up in terms of the dimension as well. So this is kind of like the summary of the quantum numerical linear algebra. So like for quantum algorithms, actually there have already been found like some speed up for certain tasks. So not all of them are in quantum numerical linear algebra, but like probably we have already heard about like the factorization that by Shor's algorithm and maybe the unstructured search or the discrete Fourier transform. And actually like from the linear algebra or applied math, so we have some algorithms for linear system, for differential equation optimization, machine learning. I think like you will learn a lot from like the tutorials happening this week. But before I move on to details, I would like to mention like two like useful resources. So the first is kind of like a website, which is called the Quantum Algorithm Zoo. So it's kind of like a list of all the available quantum algorithms in the fault-tolerant regime at the current status, and then like you can find like a very nice summary on like the task, the classical counterparts, and the quantum algorithms, and many like references. And also, like, I'd like to mention like a nice lecture notes by Professor Lin Lin, and it has been posted on arXiv. So it's kind of like I think it is probably like the first lecture notes from a mathematical perspective on quantum algorithms. Is that right? I don't know, but like I think so. So it's kind of like nice, and it kind of like summarizes like many details in the quantum numerical linear algebra. So if you want, you can just definitely like check out those two resources. Yeah. Okay, so that is like for the introduction part. And for today's talk, I think I should change the title because it is for today's and tomorrow's talk. So we will start with the basic linear algebra operations, because I'm saying that so the quantum numerical linear algebra is like using some matrix operations to perform to design algorithms. So we will start with that. We will see like the input models for vectors and matrices on the quantum device, and we will see like how to perform, for example, like matrix vector multiplication, the matrix vector addition, and the matrix multiplication on a quantum device. So we will see like how we can do that. And after that, we will use those tools to design some useful algorithms. So we will discuss the algorithms on solving linear systems of equations. I will just like cover some generic algorithms, which means that they are designed for all linear systems of equations. So like the first algorithm will be HHL, and then I'll just talk a little bit about the linear combination of unitaries and the adiabatic approach. And besides the generic algorithms, I will also talk about a little bit on the preconditioning, so which is kind of like a powerful tool in classical numerical linear algebra, but has not been like well studied in the quantum setting. And we have the eigenvalue problems, but I will not cover that in details because I think we have another wonderful tutorial happening Thursday on maybe on eigenvalues problem or on more general like variational quantum eigensolvers. So I think I will leave it to the expert on this field. And last, I will just cover some general matrix functions. So it's basically like we are implementing some transformation of a matrix. So we will discuss the function in terms of the Hermitian matrices. So the tool is the so-called the quantum signal processing and the qubitization. And we will also discuss the transformation for general matrices. And then, of course, we will go back to the linear combination of unitary to see their relations. So this is like the outline for today's and tomorrow's tutorial. Okay, so any questions so far? Okay, great. So let me move on to the first part, that is the basic linear algebra operations. So we start with the input model. So let's start with like the input model for the vectors and the matrices. I think like probably many of you are familiar with this, but we just want to like do a quick review and make sure that we are on the same page. So like the input model for the vector is on a quantum device is actually like a quantum state. So we start with the single qubit state. So the single qubit state can be represented as in like a two-dimensional Hilbert space modular like two norms. So it's like I will just use the notation cat0 to represent this vector 1, 0, and cat1 to represent the vector 0, 1. So basically, it is kind of like a orthogonal basis in your two-dimensional space. And then like a single qubit state in general can be represented as alpha 0 plus beta 1. So in the vector language, it is basically something like this. It's just like alpha in the first entry and beta in the second entry. So this is like the mathematical structure of a single qubit state. But like we have some physical meaning for this quantum state, which is like, so if we want to do some measurement on the qubit, so we will get a 0 with probability alpha square, and we will get 1 with probability beta square, which means that, so we have some restriction on this state, that is, so it should be normalized under vector 2 norm. That is, the alpha square plus beta square should be 1. But like these are the space for the single qubit state, or the input model for a two-dimensional vector. Like if we go beyond the single qubit state, we just want to like a general n qubit state. So the n qubit state, if we look at the basis, we can just represent as the tensor product of n multiple single qubit state. That is like, so we have I1, I2 all the way to In. So for each ij, they are either 0 or 1, which means that they are either 1, 0 or this 0, 1 vector. And then n qubit state can be designed by doing the tensor product between like among all these vectors. You can see that, so using this tensor product, you can really get a 2 to the n dimensional vector, which means that is the reason why we are seeing that the quantum data structure can possibly have exponential speed up in terms of the dimension, because like a n qubit state is actually representing a 2 to the n dimensional vector. So this is what we have. But like, I should mention that this state is called the tensor product state. It's only for constructing the basis. Actually, like for general n qubit state, it is not necessary to be this tensor product structure. Which means that, so for example, you can just view those kind of states as an orthogonal basis of your entire Hilbert space, and then you can just like perform some linear combination of all of these bases, and then you will just get some general state which might not be the direct tensor product of like single qubit states. But like in general, we will write this kind of cat j to be an orthogonal basis of the entire Hilbert space. So basically, like here we have a cat j, and you should understand this as something like we can have a binary representation of this integer j, and then for the binary representation for each digit of the binary representation, you can just use a single qubit state to represent that, and then like just like do the tensor product together, and that will give you like a orthogonal basis of my entire Hilbert space. But again, like so for an arbitrary quantum state, it can be very general. So, okay, yeah, this is like a general quantum state, which is the linear combination of my basis function, and in the vector language, it can just be directly written down as something like this: the alpha 0, alpha 1, all the way to alpha like 2 to the n minus 1. So it's like a 2 to the n dimensional vector. And of course, like we have some measurements. So if you just like measure the computational basis, then we will get j from like 0 to 2n minus 1. Like we will just get one value in this range, and the probability of getting j is alpha j squared, which means that, so actually like we still need the normalization condition. That is like the norm of this vector should be 1. So this is like the very quick introduction on the input model for the vectors. And actually, like for the input model of these vectors, we will typically, throughout today's tutorial, I will in general assume this state preparation oracle. That is, I will assume there exists a quantum algorithm or a quantum circuit, OU, which can map your computational basis 0 to a desired state U that I want. So this is oracle which we call the state preparation oracle. So I will take this as assumption in the tutorial, but I should mention at the very beginning that, so this is a very big assumption. So like assuming the efficient state preparation oracle is a very big assumption, because like constructing this oracle is in general hard, because like, so in the worst case, you probably have to pay like linear in terms of 2 to the little n cost, the overall gate complexity to really construct a state preparation overcall. But like if your quantum state have some nice structure, then probably the cost can be lower as to like maybe only a polynomial in terms of n. So here I just list like 2 references. So for the first is probably like the first state preparation overcalls for a probability distribution by Grover and Rudolph. So it can achieve a exponential improvement in terms of the dimension. But like I also point out like another reference, which is like a very recent paper, which gives you like a very nice summary on the current status of the state preparation of constructing the state preparation overcall. But like in general, it is like the gate complexity would be hard, but the circuit depth can be lower.
Yes.
Yeah.
So when you say this preparation, so the output state, what property does it have? Does it have the property that if you measure it, it gives you UJ, probability UJ absolute value squared?
Yeah, that's right.
Is that the only thing that you require of it, or is it actually that you're close to that particular wave function? Phase is that important for you? Or?
The phase is not important, so that is the only thing that I'm assuming. That is, if I think like the global phase is not important, but like probably I'm assuming like the local phase should be like exactly something I'm written down here. Yeah.
But then it's not possible always, right? Because you only have so many circuits, right? And so you cannot produce an arbitrary vector. You can only get close to one, right? So,
yeah, we can just only get close to that. Yeah, that's right.
So what kind of state can this paper from Grover prepare? Like,
okay, it's so-called the integrable probability distribution. That is, you need to know the CDF of the probability distribution. So for the Grover's work, you're assuming that those UJ or the square root of UJ is a discrete probability distribution, and then you know, like for example, the probability of getting maybe a number which is smaller than some capital J or something like that. You know that, and then like you can just like use the Grover idea to construct this quantum state with cost only linear in terms of n. So the idea is kind of like using the binary representation, right? You can just like start with like divide your entire interval into 2 parts and then like do that again and again. And that is why we are assuming that we need to know the probability distribution, and then we can get some kind of speed up. Yeah, we need UJ to be positive. So like for this Grover-Rudolph algorithm, it has very hard restriction. Yeah.
And you also need some smoothness.
Yes, that's right.
In general, is this type of state preparation like the main way that we get classical information into?
Of course not. Yeah, we have some other models but here I guess like this is kind of like the standard model for the linear algebra operations. So yeah, but of course we can use some other model. Like you can just try to like store your information in the register or using some other like representation. But like yeah, in general like other models are definitely possible. Yeah.
So is there any extreme case where people need maybe exponential cost to do this state preparation?
Yes, I think like there are many cases like in general, so like the cost is actually like linear in terms of this 2 to the n. Yeah, it is specified in this paper, so it is like a quite nice idea. Yeah. Okay. Yeah.
Why is it called an oracle, and why is like you say like this is an expensive operation, but this seems to me it's just an operation of take one vector to another vector. So it seems like kind of the most basic operation, but you're saying it's expensive.
Yeah. So like by oracle, we are meaning that so we are like ignoring the cost of constructing this operation. That is, we just take this as an input model as assumption. So that is what we mean by oracle. Like in the later of this tutorial, if we want to like count the complexity of the algorithm, we will count the number of the oracles that we are using. So that is why we are using this terminology oracle. But like I just want to like mention that at the very beginning is that so. Assuming the oracle is a very big assumption, yeah. Okay. Oh, the circuit depths I think like for the Grover-Rudolph is quite low, but like also like for this recent paper, the circuit depth is also low. So for example, if you have, I think the circuit depth is kind of like log. So it's kind of like the overall gate complexity is like 2 to the n, something like that, but the circuit depth is only n or poly n, something like that. So it's like a low depth algorithm with high gate complexity.
2 to the n, worst case.
Yeah, in the worst case. Yeah, that's right. Okay, great. Yeah, thanks for the question. And I didn't see that machine is working, so yeah, I'm not. I'm not sure. Like, yeah, I think that is really cool stuff. So, okay, yeah, let's move on to the input model for the matrices. So for the matrices, the input model actually like there are also like multiple different like input models for the matrices. Like we have some sparse input oracle, we have some like other structured oracle, but like. During the tutorial, I will like use the input model of the so-called the block encoding. That is like the block encoding is defined to be something like, so the goal of the block encoding is to input a general matrix into the quantum device. So it's basically like, assume that we have a matrix A, which is a 2 to the n by 2 to the n dimension matrix, and it need not to be a unitary, so it can be like a general matrices, and then like the definition of the block encoding is a larger unitary U of A, so which is in the dimension 2 to the n plus A by 2 to the n plus A, and this such that so if we only look at the upper left block of this unitary, it becomes a rescaled matrix of A. So for this is kind of like the formal definition using the linear tensor product language, but like if you use the standard like linear algebra language, you can just view this UA to be something like this. So it is like a larger matrix, and on the left upper corner, so we have A over alpha, which is rescaled information of my matrix A, and for the other three blocks, actually like at this point, we don't really care about what they are. So here like, can see that, so here, this is kind of like the input model for the matrix. We will assume this input model, but like we have this kind of parameter alpha. So alpha is so-called the block encoding factor, and it should satisfy that this alpha should be at least the spectral norm of A. So the reason is because we want this UA to be a unitary operator, which means that a sub-block of this unitary operator should have bounded spectral norm. So the spectral norm of this sub-block should be bounded by 1. Means that if we have a very large matrix A, so we want to make this oracle or this input model to be possible, we have to first like rescale this matrix. So this is kind of like the block encoding. But like in the tutorial, I will like mostly assume this alpha to be 1, just like for technical simplicity. I just want to mention that. So okay, in general, we can also do like this block. Can also assume this block encoding. Yeah.
Just a question: is the block encoding matrix unique? Or if not, what are the criteria?
Definitely not unique, because like you have some flexibility to design your other like blockings.
Right. And is there any criteria given the flexibility to choose it?
Yeah, you have some flexibility. Yeah, actually, I think like at the end of tomorrow's talk, I will discuss some specific block encoding, maybe for some Hermitian matrix, and you can see that. So if the block encoding have some better structure, then probably it can like benefit from design. It can benefit the design of some algorithms. Yeah. Okay, yeah, this is for the block encoding. And of course, again, I should mention that constructing this block encoding is generally hard. So because it means that, so if we are given a matrix, so for example, if we are given some like classical access to the data in the matrix, then I just want to ask the question like, can we really construct this block encoding? And as far as I know, so for the general problem, this is still like an open question, or like or if you use some like other oracles, so the computational cost should be in general hard. But for some special cases, actually, we can indeed construct this block encoding model. So for example, like of course, for unitary matrix, it is trivial because the unitary matrix itself is the block encoding. So it's block encoding. And also like for the sparse matrices, if you have some sparse input oracle, then there's like some efficient way of constructing this block encoding. And also like for some nice structured matrices, you can also do that. So here I just like mentioned like several references for you if you want to like learn more details. Okay, so that is.
I think even for unitary, you need it to be structured, right?
Yeah, that's right. Yeah, because you need a circuit for that. Yeah.
So what do you mean by constructing in a quantum circuit?
Yeah, directly like writing down the quantum circuit, the specific quantum circuit for the UA.
And that would depend on the gates that are everything.
Yeah, that would depend on the gates, and that is why I'm saying that it is very difficult, right? Yeah.
Are sparse matrices generally efficiently implementable, or do the sparse matrices need to have additional structure in the matrix elements?
You should have additional structure because to construct the block encoding of the sparse matrix, actually like we need another oracle, which is called the sparse input oracle. And the sparse input oracle gives the information of the, or the position of the non-zero entries in your matrix. And to construct this position oracle is in general hard. So, but if you have some structured matrix, for example, if you have a discrete Laplacian matrix or a tree diagonal matrix, that should be fine. Yeah.
We add like a lowercase a extra dimensions. I forget, was there something that determined what A was? Like how much larger we have to make this matrix to turn A into UA?
Oh, I don't think there is like a definite answer. So, but like you should make it to be larger. But I mean, it can be much larger. You can just use like many ancilla qubits. So, yeah, I don't think there's like a general answer to that question. It really depends on the specific matrix A.
N is enough, right? I mean, if you double this, the size, it's...
Oh, yeah. If like from a theoretical perspective.
One, I mean...
Yeah, one is like, the dimension.
The dimension of the space.
The dimension like 2 to the n plus 1 by 2 to the n plus 1 should be sufficient, but that might not be very efficient on a quantum to construct a quantum circuit. So yeah. Okay. Yeah.
You said that larger is better. Why is larger better?
No. Sorry if I said that. Apologies. So it is not like larger is better. Actually, like it's. I don't think larger is better. I just feel like so it just like for a specific purpose. So it's kind of like, I mean, it really depends on the specific matrix, and I just feel like, actually, like I think like smaller is better because like if it is smaller, then you're using like less quantum resources to construct this unitary.
I think it's more like if you're allowed to have more ancilla qubits, then you have greater freedom in terms of constructing circuit, therefore you can probably get lower cost.
Yeah, that's right. It's kind of like a trade-off. If you have like more like spatial resources, you can probably like save your computational cost. Yeah. Okay, great. Yeah, that is for the input model of the matrix. And then I'll just like start with the first algorithm that we have for the tutorial, which is the matrix vector multiplication. So I just put like a mark on this algorithm because it is not a real algorithm. It's kind of like a very simple like application, but I just want to start here and I just want to like go through all the details like slowly to make sure that okay we can start to like get familiar with all the notations and all the informations right here. So for the matrix vector multiplication, actually like the algorithm is that we can directly apply the block encoding to a quantum state. So again, like a review of the input model, that is we have the block encoding of A. So here basically like I have like 3 like equivalent languages for this block encoding. And here like for simplicity, I'm assuming that this matrix is a 2 to the n plus 1 by 2 to the n plus 1. That is I'm only using like one more ancilla qubit for this block encoding, but like this is only for technical simplicity. So basically like we have block encoding defined to be this, and also like it is on the left upper corner of the, my matrix is on the left upper corner. And we can also write it down as a this kind of like tensor product form. That is, if we have 0, 0, then this corresponds to the this block A over alpha. And for the 3 other blocks, we don't really care about those. So these are like 3 kind of like equivalent languages for the block encoding. And we have a quantum state, which can be viewed as a 2 to the n-dimensional vector. And then the algorithm of matrix vector multiplication is that we apply the block encoding. So this is the quantum circuit for this algorithm. So like if you're not familiar with the circuit, that should be fine. The circuit is just like you are like describe the operations on the corresponding qubits or on the corresponding like subspace by this kind of like picture. That is like we have a 0 to be the ancilla qubit, which is like 0 corresponds to like this part, and we have a u which corresponds to the system part. That is like this u is a 2 to the n-dimensional vector, and then like by this ua, I'm meaning that I'm applying this operator on the entire space. So this is I put this ua here, and then like and this thing is the measurement. That is I measure the ancilla qubit to get a result. So this is the circuit, and in the mathematical language, you can write down it as something like this. That is, I'm applying UA to 0 tensor product U, and then to check this equation, it is a little bit more convenient to use the tensor product representation because you can see that. So if we take the first part, 0, 0, tensor A over alpha, then we will have like bra A, bra 0, cat 0, and they will be 0, and then we have another 0 remaining here. So basically, like we are doing nothing on this ancilla qubit, but for this system register, we are applying my matrix A over alpha. And for the remaining part, so I will possibly have some ones, but like I really don't care about what this state is. Or equivalently, so if you are like not comfortable with this notation, then you can also think this block encoding in this like matrix vector language. That is, we have a block encoding A over alpha and some like other blocks, and we have my quantum state U, but like this 0 tensor U can be written as something like U0, which is a 2 to the n plus 1 dimensional vector. And we have like U to be 2 to the n dimensional vector, and we have this 0 representing another like 0 vector for the 2 to the in the 2 to the n dimension. And then like can see that, so it is just a matrix vector multiplication, and then if you just compute the first half of the output state, it just becomes like A times U normalized by this vector alpha, but we will have some junk state right here, so we don't know what they are. Okay, so like after applying the block encoding, then we can see that, so we have a superposition. We have a superposition between the desired state and some like other state that we don't want, which means that we need some post-selection. We need some measurement to get the desired part that we want, to get this A times U. So the way is just to do this measurement. That is, we will measure the first ancilla qubit, and then if the outcome is 0, then the remaining part would be exactly this kind of A times U up to some normalization constant, which means that we succeed. But if the outcome is 1, then we fail, and then we have to like start over and do the entire circuit, although there's only like one oracle there. But we have to do the entire circuit again and do the measurement again, and we repeat this procedure until a success, until that we get a 0. So this is like the idea of matrix multiplication, and you can see that it is kind of like different from the classical numerical linear algebra, because like we have some kind of like success probability, we have some kind of like overhead due to the measurement. It's like, so because like the success probability is just like the magnitude of the first part, so the success probability can be written down as this A times, the norm of A times U divided by alpha squared. So it's like, this is like the success probability. And if we want to get a succeed, then we have to like repeat, and the expectation value of the repeats should be like the inverse of the success probability, which is alpha squared over A times U squared. But here, in general, so like in many quantum algorithms, we will just say that, okay, the number of those repeats is sufficient to be a square root of the inverse of the success probability. So this is like because we are applying some technique called amplitude amplification, which is a generalization of the Grover's algorithm. But like I will cover the details at the end when we talk about the singular value transformation. But like you can just imagine that. So, but like anyway, so for this matrix vector multiplication, we have some actual factor. We have some like number of repeats, which is like completely different from the standard like deterministic classical algorithms. Okay, so like this is for the matrix vector multiplication. And I will just move on to the next algorithm, which is the matrix addition. So this can be implemented by a very powerful technique called the linear combination of unitaries. I should say that, so this is probably one of the 2 most important algorithms in my tutorial. So this is like, because like it really has like many like applications on designing different algorithms. So this linear I'm sorry. Yeah.
I just wanted to get this before we move on, but like, yeah. So you said that so this block encoding is expensive, but not so much if the matrix is unitary, if A is unitary?
If it is unitary, or if you have a circuit for that unitary, then actually like the block encoding is trivial, because
But so isn't state preparation just a unitary matrix applied to the ground state?
It's like okay, yeah, so like we say that the block encoding for unitary is trivial, we are meaning that. So we need to assume that unitary to have a specific circuit implementation. But like for the general state preparation oracle, so probably we don't know the circuit before the quantum state. So
because you'd have to have a different circuit for any
probably like
arbitrary
we have different circuits for different unitaries, and some of the circuits are simple, some of the circuits are very complicated. Okay, yeah, great. Okay, so yeah, let's continue with this. The LCU, the linear combination of unitaries. So the task of this LCU is, as its name suggests, it is just like implement a linear combination of the unitary operators. That is, we have many unitary operators, uj, and we have some coefficients, cj, so they can be complex numbers, and then like we want to compute or we want to like construct a block encoding of this, the linear combination. So okay, yeah. The first thing is that we should note that this linear combination of unitaries is not necessarily unitary. It can be a general matrix. So that is why we want to construct a block encoding of this matrix instead of just like a quantum circuit for that. Okay, so like the linear combination of unitaries was first proposed by this paper by Charles and Webb on like Hamiltonian simulation tests, and also like it has been applied to many other quantum algorithms. So, but like here, let me just like go to like the basic idea of the LCU. So, like to discuss about LCU, I would always like to start with the toy example. That is, we just want to compute the linear combination of two unitaries. Okay, and uniform superposition of the uniform combination of two unitaries. That is, we have u0 and u1. Want to compute like half of the average of u0 and u1. So this is the algorithm. So the algorithm is that, so we have a quantum state u0, and then we use one more additional ancilla qubit, which is 0 right here. And then like what we will do first is that we will first apply so-called Hadamard gate on the ancilla qubit. So the Hadamard gate is a matrix, it's a 2x2 matrix specified here. It's 1, 1, 1, -1 divided by square root of 2. So you can check that this is a unitary matrix, and it can map your the zero basis to a uniform superposition of 0 and 1, and it can map 1 to like 0 minus 1 divided by square root of 2. So you can just check that this is like a unitary operation. And if you apply a Hadamard gate on the ancilla qubit, what we will get is that we will change the ancilla, this 0 value in the ancilla, to be a uniform superposition between 0 and 1. That is, we will have this 0 plus 1 in the first ancilla qubit. So this is after the first step. And then what we will do is so-called the controlled operation of the unitaries. That is, we will do the controlled operation of u0 and the control operation of u1. So by control, I mean that. So whether we are performing u0 and u1 depends on the number or the value in the ancilla qubit. That is, if the ancilla qubit is 0, then we will apply u0. And if the ancilla qubit is 1, then we will apply u1. So this can be written down as the circuit like this. So, and then like after this controlled unitary application, what we will get is that, so you can see that, so for the first half, we have a 0 in the ancilla qubit, and then we will apply our u0 on the state vector on this u0. And for the second half, we have 1, and then we will apply u1. So this is the quantum state that we get after the controlled version of these unitaries. And then the last step, or the second to the last step, is that we will apply another Hadamard gate. That is, we apply a Hadamard gate on the first ancilla qubit, and you can check that. So applying this Hadamard will like map this 0 to superposition of 0 and 1, and map this 1 to something like 0 minus 1, and we will get a quantum state which looks like this. So for the 0 part, we will get half of u0 plus u1. It's really because we have this u0 from this 0 ancilla qubit, and we have a u1 from this 1 ancilla qubit by applying this Hadamard gate. And of course, we have some orthogonal state right here. And after this operation, we can see that, okay, like now we have something similar to the case when we apply the block encoding, right? It's like when the ancilla is 0, then we have the desired quantum state that we want is the average of u0 and u1, but we have some junk state. And then the last step is do the measurement. That is, we will measure the first ancilla qubit, and then, okay, if we succeed, then of course, we succeed. So if we get 0, then we succeed. And if we get 1, we just redo all the circuit and do the measurement again. OK, this is like a toy example of the LCU for like combining 2 unitaries. So what if we have like multiple unitaries? And then like the circuit will be very similar to the special case. I just specified this on the right. That is, so we will like, it still contains 3 steps. So first, we will do so-called the prepare oracle, which is a state preparation oracle. That is, we have some coefficients Cj, and then we assume that we have a state preparation oracle which can give me the quantum state encoding the square root of Cj in its amplitude. So it has to be normalized. So basically, we have to normalize everything by the y norm of the coefficient vector. So this is like the prepare oracle. And if you go back to see the toy example, this Hartmann gate is actually acting as the role of this prepare oracle in the general case, because like on the left-hand side, our Cj's are, we have C0 equals C1 equals half, and then like what we need is that we need to map 0 to 1 over square root 0 plus 1 over square root 1, which is exactly this Hartmann gate. So yeah, this is like for the prepare oracle. And then after applying the prepare oracle or that Hartmann gate, we have so-called the select oracle. So the select oracle is written down as this form. It is like a controlled implementation of the unitaries. That is, if my ancillary register is J, then I will apply my unitary UJ. So this is what we call the select oracle. And then like you can see that a toy example of the select oracle is basically like right here. That is, if we have 0, I apply U0. If I have 1, I apply U1. And then after that, I will apply a prepare oracle inverse. So I just apply the inverse of this unitary, and then which is also this Hartmann gate, because like for Hartmann gate, this inverse is itself, and then I just do the measurement. So this is the general LCU oracle. So you can just view this as a generalization of the single case, and I think I have some detailed calculation showing you that what is the quantum state of each step. So as I mentioned, like we start with 0, U0. And if we apply the prepare oracle, then actually we are creating some superposition in the ancillary register. So imagine that in the toy model, we will have a superposition between 0 and 1. But here we have a general superposition. And then like we have this superposition, then like we apply the select oracle, then like which means that we have J in the ancillary, then we're applying UJ. And then we apply this OP Dagger, or like it is just the inverse of this unitary, and then like we will get something like this. But like the last step needs some like mathematical elaboration. So probably you can just check this by doing some calculation back forward. But like we have this equation, and then you can see that. So here what we have is in the first half of my quantum state, I will have the linear combination of my unitaries divided by some normalization factor. So this is the LCU, and it is quite straightforward. But okay, is there any questions so far? Yeah.
So the prepare oracle is, I guess, as hard as the state preparation oracle.
That's right. In general, it's as hard as the state preparation. Yeah, that's right. Yeah, if your coefficients are very complicated, then yeah, it should be, the cost will be like something like linear in terms of the numbers of the unitaries that you are combining. But like for some specific case, of course, it can be like easier. For example, if all the coefficients are y, you can just use like the Hartmann gates, right? Yeah. Yeah.
Also, usually, like we're not combining exponentially many unitaries.
That's right. Yeah. Usually, the number of the unitaries are not very high. Yeah.
Yeah. So in your equation, when you write this orthogonal notation, do you mean that it's only orthogonal in the ancillary qubits?
So you're meaning like this equation, or?
Yes.
Okay. I'm meaning that there's some like superposition in the ancillary qubit. That's right. Yeah.
Yeah. So I want to ask for that orthogonal notation. Do you mean that?
Oh. Yeah, that's a good question. Sorry, I forgot to explain this. This means that this represents some quantum states or some like superposition of quantum states where the ancillary is not 0. Yeah, the ancillary can be 1, can be 2, can be whatever you want, but it cannot be 0. And I don't care about the remaining part, the second register. Yeah.
So in like the trivial, the toy example with like the Hadamard gates, So you get, if the ancilla qubit is 0, you get the desired U0 plus 0, 1 gate.
Yeah.
But in the other case, you do get something. You get the U0 minus
Yeah,
U1.
yeah, that's right.
And then like clever algorithms that like, make use of that, like, because you kind of get, like, you call it the success probability if it's 0, but really you're just getting like a different operation that might be interesting.
Yeah, that's right. Yeah, for the toy example, that's right. But like in the general case, because like this kind of like ancilla can be like very complicated, and furthermore, for the state preparation oracle, actually we only assume that it can map 0 to the superposition of something like this, which is definitely not unique because like we probably have a high dimensional unitary, and we only assume like one condition on this unitary, which means that for the orthogonal space, actually we don't know anything. For example, we don't know what this oracle will map 1 to, like, we don't know like what this oracle will map 1 to somewhere else, and like probably like that will depend on like the specific like construction of your prepare oracle. But like in general, we will just directly measure this. We will just view this 0 as a success.
Okay. Yeah. So if you have a circuit for each u sub j, is it like trivial to build the select oracle efficiently, or?
Yeah, that's a great question. I'm about to discuss that. So it is not trivial because like you can imagine that. So a trivial way is to like implement this control logic in a straightforward fashion. That is, you just like for each unitary, you just add another layer for your control logic, and then you implement like these unitaries one by one. But that can be very complicated. Actually, like there's some like better way of implementing this select oracle, but we need some further assumption. That is, so for example, if all of these unitaries have some relations. So for example, if uj is the power of a single unitary, let's say if uj is something like, I think like I can write something here. Let's say if my uj is something like v to the power j, where v is another unitary or another efficiently constructed unitary, then actually this select oracle can be much easier because like you can use a binary representation of this power j and then just apply your control logic according to that binary representation, and then like the overall complexity will still be like linear in terms of the number of the unitaries that you're applying here. Yeah, so the short answer is that it's a great question. The cost depends, and in general it can be expensive, or it depends on like the number of the unitaries and the cost of implementing each unitary. But in some specific case, and you will see that in many applications, actually we have some nice structure and it can be simpler.
Maybe I had a remark that the construction of the prepare oracle is a very important topic, and there has been a lot of interesting progresses recently. I believe San Carlo, who's here in the program, and he and collaborators has a recent paper on this, and be already an interesting topic to start discussing that.
Okay, yeah, great. Yeah, thanks for the remark.
So how bad can the select oracle be?
Okay, the worst complexity is just like the overall complexity will be the summation of all the complexity for each uj. So that is the worst case, right? It can be, if for example, because like constructing each uj can also have like different complexity. So for example, if like for each uj they are similar, and then like the overall complexity would just be something like j times the maximum cost of uj or something like that. That is the worst case.
Is it ever the case in practice that the one norm of the coefficients like is a very, very large upper bound to the like spectral norm of the linear combination of unitaries?
Yeah, that's a great question. Yeah, this is possible because like here actually we are considering some like, yeah, the worst case scenario, right? It's really like due to like this implementation of the prepare oracle, and then like, yeah, it can definitely like overestimate the actual, the spectral norm of this CJ UJ. So I think like that is like probably like one drawback of the general linear combination of unitary algorithm. Yeah, but like you can see that, so it can be somehow like improved according to these factors on the denominator, because like if we just like measure this ancilla qubit, then like the success per all the number of the repeats should be like the one norm of this C vector divided by the norm of this this operator acting on your input state. That probably this can somehow like cancel some like scaling in your like, yeah, in your one norm. Yeah. Okay, great. Yeah, that is for LCU. And the LCU is a very important subroutine, and And in the tutorial, I will just like use this LCU at least for 2 more times. So one is for solving linear system, and another is for performing general matrix transformation. But like this is like the general framework of LCU. And then so far we have seen that so we can do the matrix addition for unitary matrices. So what if we have non-unitary matrices? And then like the idea is quite simple. We just use the block encoding. Right? Because like we just like if we want to like compute like or we just want to construct the block encoding of the linear combination of general matrices, and then like what we should do is that we should just like replace the matrix by the corresponding block encoding and then perform the LCU circuit again. But like at the last we need some measurement. We will measure both the ancilla register for the LCU and also like the ancilla register for the block encoding. And here, like I'm assuming that for all the block encodings, they have the same number of the ancilla qubits, which is like a small assumption because you can always consider the worst case. That is, you can just always add as many ancilla qubits as you want. So
this is the best you can do. I mean, you cannot just simultaneously dilate the row of A's and then make one big block that dilates them all at the same time. I mean, something which you measure between like, I and J or something like this, you get the J thing.
I think this should be equivalent to the LCU, right? Because like I feel like this blocking or, you are saying that so have like a single block encoding for multiple matrices, right? Oh, that's an interesting idea.
You just take a row of A's instead and you dilate that at once, and then your OP would then be adapted to that as well. So I don't know if it's equivalent or not.
Oh, I see. Yeah, that is interesting. I haven't seen that before. So, any comments from the audience or?
I mean, this is to put the AJs
on the diagonal. Yeah.
And this is to put on the same row. I mean, it's not quite clear. I mean, to me, one is better than the other. Maybe they're just equivalent ways.
Yeah. Yeah, but I'm thinking.
So one's a JJ, the other is a 0J. So construction cost.
Yeah, but I'm thinking like so probably the suggestion is that so we're using the a single ancilla or single ancilla register. It's because like here actually we are not putting AJs on the diagonal. We are putting U of AJs on the diagonal, which means that we are repeating the ancilla qubits or something like that. Okay. Okay, yeah, that is. Oh, yeah.
Sorry, I missed the point where, what's the number of terms that we can handle in the linear combination?
Oh, I didn't specify here. You can just imagine it's capital J or something like that.
So yeah, is there a limit? Like what? How many?
Yeah, that's right. Because the cost of LCU will depend on the cost of constructing this prepare oracle and select oracle. So if like the number of the coefficients are large, then probably like constructing this prepare oracle will be expensive, right? And also like for the select oracle, if you have more unitaries, then it can be like more involved.
I guess I'm asking, like, what's the theoretical limit?
Okay, the theoretical limit. So it's yeah, that's a good question. I think like even for the selector, it is still kind of like an open question. Like in general case, it is not open question. Like in general case, in the worst case, it's just like linear in terms of the number of the unitaries that you want to implement, but like you want to combine. But like, can we do better than the number of the unitaries? I think it still remains kind of open because it really depends on the structure of your each unitaries and like many other like all the cost of implementing each unitary. Yeah. And also, like for the prepare oracle, it just goes back to the state preparation problem.
So, what are some special cases where select oracle is cheaper than the worst case?
Okay, yeah, I think like you will see that later in solving linear system. But like one specific example is what I mentioned here is that if your matrix is just like the power of a single matrix, that would be like much simpler. Because like you can imagine that if your matrix is U to the power j, then the cost would be, let's say, if the cost of implement this U is, let's say, C or something like that, and then like you have to like, the cost is not only J times something, it is like you have to sum all of your terms, that is have to sum like say maybe 2C, 3C, blah, 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 then it will sum up to something like J squared or something like that. But if you have this relation, then like the cost will be actually linear in terms of J. Okay, yeah, great. Yeah, that is for LCU. So a slight generalization of LCU is that we know how to do the addition among matrices, and then like a slight generalization is that how we can do the addition among vectors or among the quantum states, right? So it's like, it is like again, the LCU, but like we just replace the unitaries by the corresponding state preparation oracles, right? Because like for the linear combination of vectors or for quantum states, we just want to combine those Cj, Uj, and then like if we have the state preparation oracle, then what we are doing is that we just apply this linear combination of unitaries on the input vector to be the 0 basis, and then like we can do the linear combination of vectors. I should say that that is not quite useful because I think like compared to the linear combination of unitary. Okay, so we have finished the addition, and then what we are doing is the matrix multiplication. So like for matrix multiplication, let's start with two matrices. Let's start with two unitary matrices. Of course, like for two unitary matrices, it's quite straightforward. That is, we have an input state, and then like we apply my U0 if we have a circuit for that unitary, and then apply U1. But like the interesting thing is that, so what if we have two general matrices? That is, if we have A0 and A1, and I'm assuming the block encoding of A0 and A1, so what can we do? So remember that in the matrix addition, we just directly replace the unitaries by its block encoding. But here, can we do the same thing? So actually, like we cannot do the same thing because like if we just directly replace the unitary by its block encoding and use the same ancilla qubit, then actually like the second application of the block encoding will destroy your first quantum state. So the reason is that, so let's see. So this circuit is performing a quantum state that is UA0 acting on a state and followed by this UA1. Let us first do the first operation. That is, we are applying this UA0. What we will get is that we will get A0 U0 correspond to this 0 ancilla part, but we will have some junk state. That is, we will have some state correspond to this 1 part. And then the issue is that if we apply this U1, we can see that applying this U1 to the first half will give me the correct state, but we still need to apply this U1 to the second half, and this second half will give me something that I don't want, will give me some junk state back to the 0 part. And if you want to understand this like in the matrix language, I think I have a typo right here. That is, let me change that. Okay, so like if we just see this in the matrix language, so that is, we have a block encoding of A0, have a block encoding of AY. We just like apply this A0 on my input state U0, 0. And then what we will get is that, so for the first half, we will get A0 times U0. But for the second half, we will get this blocking acting on U0, which is some junk state. And here you can see that if we do the next computation, it will be A1, A0, U0 plus some other things that we don't know and we don't want. So this does not work. And then we have to fix this issue. So like there are like multiple ways of fixing this issue. So there are some, of course, like the most like simplest, the simplest way would be like you just like apply U0 and do the measurement, and then apply U1, then do the measurement, so on and so forth. But that would be like a bit difficult to really implement this kind of circuit. We just want to like postpone all the like measurement to the end, and then like, so what we will do is that, so one way is to duplicate the ancilla qubits. That is, instead of using a single ancilla qubit, we just use multiple ancilla qubits. And then if we're using multiple ancilla qubits, so like for each ancilla qubit, it is only for a single application of the block encoding. And yeah. Oh, it is not hard. It is just like the circuit would become like, it would become some kind of, because like suppose that you have a real quantum devices, and then like you just perform one action and then you do the measurement. Okay, I will just see the result and decide whether I move on or I just like restart, and that would be like hard for our human beings. So it's just like, it's not like in general hard for the complexity. Yeah. Okay, yeah. So we will like do this kind of like the duplication of the ancilla qubits, and then like, you can see that, so here for the multiplication of two unitaries, we use two ancilla qubits. We have a 0, we have another 0, here I have we have a I have a subscript 0 and 1, which is indicating like which kind of like blocking coding it is corresponding to. So it's basically like we have like 2 ancilla qubits, and then we will apply my blocking coding of a 0 using my first ancilla qubit, which means that it will create some superposition according to my ancilla qubit labeled by 0. But after that, I will apply my blocking coding of UA1 corresponding to like the ancilla qubits labeled by 1, which means that, so you can see that this 0 was not destroyed in the first application of the blocking coding, which means that it is still safe to apply another unitary according to my new ancilla qubit. And then like after that, what we will get is something like this, which means that, so I will have my desired part, A1, A0 acting on U0 if all of my ancilla qubits are 0. And I will have some junk states. So they are indicating that, so which kind of step, they are indicating the success of some specific step. But like what I'm going to do is that I'm just going to like measure all the ancilla qubits. If I get all zeros, then I succeed at that. I can do the multiplication for 2 matrices. Yeah, this is like a, yeah.
I was just wondering, so in this case now you have like 2 ancilla qubits you have to measure for the success probability.
That's right.
Is that like multiplicative or like additive in how the success probability decreases?
They are multiplicative.
Okay.
Is there any other question? Okay, yeah, great. So this is for the multiplication, but this is only for the multiplication of 2 matrices, and you can imagine that if we have multiple matrices, and then what we have to use like multiple ancilla qubits, right? So we have to like, because like for J matrices, for each blocking coding, we need an ancilla qubit. So like for multiple matrices, we need many ancilla qubits, which can be like expensive, like for the space resource. But like there's like another method which can save the number of the ancilla qubits, which is called the compression gadget. So it's kind of like, it is like a little bit involved to discuss, but let me try to do that. So like the idea is that, so let me go back to the previous slides. In the previous slides, so by duplicating the ancilla qubits, actually like we are using more space resources to indicate the success of the blocking code of each blocking coding separately. But here, like in the compression gadget, actually we are using like another like counter register to indicate the success of each of the application of each blocking coding, and then like we can use this counter to indicate like if this counter is reset to be 0, then like we have success on like all the blocking coding. So let's walk through this this quantum circuit. So in this quantum circuit, actually like so first we only need one extra ancilla qubit, and we need another operation which is called this add operation. So this add operation, you can view this as some kind of like a perturbation on your ancilla space. That is like this add unitary is mapping 0 to 1, 1 to 2, 2 to 3, blah blah blah, and j minus 1 to j, and it is mapping j back to 0. And for all the remaining part, if there is, then it can be arbitrary. So like this is like the add oracle, and then what we are doing is that, so first on the counter register, we just apply this add oracle to the power j, which means that we are kind of like setting this counter oracle to the value j. And of course, we will apply my first blocking coding, and it becomes something like in the counter register, we have a j, and then like in the ancilla system, we will have a superposition between 0 and 1. And after that, what I'm doing is that I will use the information in the ancilla register to change the information in the counter register, which means that if I have a 0 in the ancilla, then I will like subtract by 1 in this counter register. Or if I have 1 in this ancilla, then I will do nothing. So which is called this controlled add dagger. Which means that, so it gives me this quantum state. That is like if I have 0, then I just set this counter to be j minus 1. If I have 1, I just this counter to be 0. So you can see that. So what we are doing here is we are transforming the information. That is because like in the first step, the information of success or failure is contained in this ancilla register, which will be destroyed later. But before we perform next application of the blocking coding, we transfer this information back to the counter register, which means that if this counter register is j minus 1, then it was a success in the previous step. And then like if it is J, then it was a failure. So after we transfer this information back, then what we are going to do is that we are going to apply another like block encoding like U1, and then you can see that, so when we apply another block encoding of U1, so for the part corresponding to J minus 1, it will be the standard block encoding application, because like for the part corresponding to J minus 1, it only has this 0 value. And we have some junk states, so we don't really care about what they are. And we are doing the same thing. That is, if this step is also a success, then we will minus 1 in the counter register. What we will have is right here, and you can see that, so after 2 steps of the block encoding, in the counter register, we have J minus 2, we have J minus 1, we have J. But like only the part corresponding to J minus 2 is a success for the previous 2 steps. And then like we can just do this again and again, and until the end, what we will get is something like this, which is that, so for the counter register, we will have a 0, and then the corresponding part will be the desired multiplication. But for we have some junk state with like different value of this counter register, and then like we just like do the measurement on the counter register, and then like if we get 0, then we succeed. So this is like a little bit involved idea of doing matrix multiplication, but the advantage is that it can really save some like space resources. But like, yeah, this is kind of like the idea for the compression gadget. I think I have finished like the basic linear algebra operation. So here's like a very quick summary. That is like we discussed the input model of the vectors and the matrices. We have block encoding, we have quantum state, and we have matrix multiplication. That is, we just directly apply the block encoding to the quantum state. And for the addition, we need to do the LCU, and for the multiplication, we have like several different methods. So yeah.
One question. So for the first page, so what's the cost for this add oracle?
Oh, the cost of this oracle is polylog in terms of this capital J, because it is acting on the log number of this qubits. Yeah.
You said that when failure happens, what happens when you fail after?
Oh, when fail after that, then you will also like subtract by 1 in your like counter register, but because like the counter register is larger in the previous step, so it will never reach 0 at the end. Because like the only situation where the counter register is set to be 0, which is the situation where all the block encodings are successful.
Okay, so if you do have a failure, you just run the entire circuit.
Yeah, that's right. If you have a failure, just like run the entire circuit and perform the measurement again.
Okay. So can't you like stop early and start?
I think so. Yeah, you can definitely do that to save some resources. Yeah, definitely.
But wouldn't that involve adding measurement gates?
I think so. Yeah, just like adding some measurement operations. But that is definitely possible. You can just like stop whatever you want. So for example, just like if you just want to stop like here, and then you can just like see if you can get a G minus 2, and then that will indicate that the success for the previous 2 steps, and you can just decide what to do next. Yeah, that is possible. Yeah.
And if you add a measurement gate in the middle of the circuit, does that collapse the state in effective computation?
I don't think so. It will not collapse the state for the auxiliary and the system, especially for the system, but it will collapse the states in the counter register. Yeah.
Okay.
Yeah.
So I think the point here is that you don't want superposition counter register at all. Right?
Yeah, that's right.
You only want one state.
Yeah.
What's the normalization factor here? It looks like this is.
Oh, I'm assuming that all of the spectral norm are bounded by 1. So I'm just like assume this for technical simplicity. Yeah.
So here, my question is about like in today's world with our noisy quantum computers that we can rent in the cloud, like to what extent are these basic numerical linear algebra algorithms, usable?
Oh yeah.
Can we actually do them? How many repetitions do we need to do? Or does it just not work yet?
Yeah, that's a good question. Like I think it's probably more suitable for offline discussion, but like my quick point of view is that so all of the algorithm that I introduced today is on the fault tolerant regime. That is not quite suitable for NISQ. But like I think like they're like like I think because Lin is here, so actually like for the block encoding, actually there's like another point of view of the block encoding, which is the RecBAM. That is like you can view a given circuit as the block encoding of another matrix, and then that is possible to be, that is probably like useful for like testing like the NISQ quantum devices or something like that, but it's kind of like a different point of view.
And not only RecBAM, the random matrix, but recently with the advancements of hardware, the Quantinuum people have done some block encoding based techniques with some classical optimization to do block encoding on actual hardware, even implement in QSP. I believe that's quantum signal processing. I believe that's a paper either published or soon to be published in PJ Quantum Information. So the short story is a long shot to really do all of these things, but the people are making it.
So if I understand correctly, by some modification of this, you can apply an arbitrary non-commutative polynomial to any arbitrary number of A1 to AN, right? So you can do like A1 times A2 plus A3Q plus, anything like that, right, in principle?
Yeah, in principle, yes.
Now, but can you go beyond that? Can you do rational functions?
Okay, yeah, it is possible. Like there's like it is called like the fractional query to the unitary. So let's say like for example, we have a unitary want to compute like maybe u to the power alpha, where alpha is like a real number or something like that. So that is possible because it is kind of like a general matrix transformation, and I will just discuss maybe tomorrow using like some polynomial expansion-based algorithm, but that is possible.
No, but I was talking specifically about rational functions, not so it being exact, not an approximation.
Okay, being.
Well, one possible rational function is A inverse or AX
yeah.
which is
A inverse.
Right. No.
But that is still
that's
like.
why I'm asking. The reason is that there is this thing which is that if you take a number of matrices and you want to compute an arbitrary rational function, then you need the following operators: put this into a larger matrix, so do some kind of block encoding, and then be able to take the inverse of that, and then multiply by some vector, which is kind of like measurements. Then you can compute an arbitrary rational function. I'm just wondering if this is kind of an equivalent language to that, where inversion is just replaced by this, this encoding as a unitary.
Yeah.
Okay.
So why don't we postpone this discussion?
Yeah, and I think like that will be my first topic for tomorrow's tutorial. It's like I'm just like going to like this is my topic for tomorrow's talk. So it's probably